So I'll talk about rheology and thermal state of Titan's crust, potential role of methane clatrate. So this is Titan as it is passing by Saturn, and Titan is Saturn's largest satellite. This satellite is particularly interesting because it is similar to Earth in a number of ways. It has a nitrogen atmosphere like that of Earth. It also has seas, lakes, rivers. However, the fluid phase is methane and ethane, unlike Earth. And methane is also the second most abundant atmospheric compound. And it's predicted that due to ultraviolet radiation and Saturn's magnetospheric electrons, the methane should be destroyed in 10 to 100 million years. Therefore, we need a long-term or constant source of methane. Previous works suggested that Titan has a convecting crust with extensive cryovolcanism, which could provide a mechanism for methane outgassing. However, recent works based on gravity and topography data suggest that the crust should be conductive and rigid, exceeding 40 kilometers in thickness, and at the same time it should be technologically inactive. Hemingway et al. Put forward this model where you can see a low density root which should to keep it in place. They hypothesized, or they put for a rigid ice shell. To explain this rigid and conductive shell, they mentioned low temperature internal ocean, low heat flow, or clatters in the crust. And only methane clatter in the crust provides a mechanism for methane in Titan's atmosphere. So what is methane clatrate? So you can think of methane clatter as a kind of ice where methane is trapped within a cage formed by water molecules. And methane clatter is significantly different from water ice in terms of viscosity and thermal conductivity. Methane clatter has relatively higher viscosity, which is 50 times more viscous than water ice. And also, it has low thermal conductivity, which is 9 to 25% of water ice, depending on temperature. So our hypothesis is that ice-clattered mixed crust can be rigid and conductive over thicknesses predicted for Titan, which is greater than 40 kilometers. So we used geothermal and lithostatic models to determine the maximum crustal thickness for a crust in thermodynamic equilibrium with the internal ocean, considering 5 different compositions: pure water ice, 10 to 50% methane clatrate, and pure clatrate. We needed to find the value. So we also considered 2 different initial conditions. We considered warm belt ocean, and also we considered cold salty ocean, because recent works shows that the ocean is quite salty. These temperatures at the base of the crust are important because they also constrain the thickness. And to construct the geothermal and lithostatic models, we needed to calculate thermal conductivity as a function of both temperature and percentage of clatrate. We did it using methods from Root, Elwood, Madden, and White et al. So this is what I found. Here you can see these dotted lines represent the stability field of hydrate in a warm belt ocean and in a cold salty ocean, and these 2 are water ice melting curve. So this one is in warm belt ocean, and this one is in NaCl and H2O system. And from these, we can constrain the maximum thickness for a particular composition. For example, here you can see for a pure methane clatrate, the maximum thickness could be 22 kilometers because methane is going to dissociate beyond this thickness. Likewise, in the case of a cold salty ocean, we have a thickness of 48 kilometers for 50% methane clatrate. Similarly, for water ice, we have a thickness of 77 kilometers in warm belt ocean. In a cold, salty ocean, we have 73 kilometers. So that is, hydrates are stable on the left side of these two curves, and water ice is stable on the left side of these curves. Now, to constrain the maximum conductive thickness, we used stagnant convection model from McKinnon, and which has been previously used in other isosatellites, including Titan. So in a stagnant lead convection model, we have a conductive stagnant lead overlying a convecting sublayer. And to find the maximum conductive thickness, we modeled Rheolo number. And Rheolo number is a dimensionless quantity that tells if it is convecting or conducting. I mean, if conduction or convection is a dominant mode of heat transfer. So if Rheolo number is less than the critical Rheolo number, we have conductive stagnant lead, and when the Rheolo number exceeds critical Rheolo number, we have convecting sublayer. So here we model the Rheolo number with crustal thickness. Here, these horizontal lines are critical Rheolo numbers, and these vertical lines represent corresponding thicknesses. As you can see here, and this X, uppercase X, represents the depths of melting. So here you can see all the compositions are stable within the conductive region. So here, critical Rheolo number is a decisive factor. Therefore, from a thermodynamic equilibrium, so thermodynamic equilibrium predicts that stagnant lead convection is likely except for pure Clathrate. And again, in the cold salty ocean, geothermal gradients are the decisive factors, because you can see the Rheolo number, before reaching the critical Rheolo number, the compositions start to melt. Therefore, here, thermodynamic equilibrium predicts that only water ice could convect, all other composition lead to rigid and conductive crust. So here I just wanted to show how much carbon we need, how much carbon of Titan's total carbon budget we need to form these to have crusts of these compositions. And now considering the 40-kilometer cutoff, we have these compositions, and which requires less than 7.5% of Titan's total carbon budget, which is feasible. And this kind of summarize our findings, but this is not the summary. Here you can see, as we add methane clathrate, the crust gets thinner, which is expected because addition of methane clathrate decreases the thermal conductivity, which causes heat to build up, that is, crust to melt. And in the warm-damped ocean, again, we can see stagnant lead convection is possible. However, in the cold salty ocean, we see only conductive. Only conductive crust. And here you can see also that with the addition of methane clathrate, the crust gets thinner, which is also as expected. So here are my conclusions. Mixed ice clathrate composition may explain a moderately thick, rigid, and thermally conductive crust. Based on chondritic models of Titan's accretion, less than 7.5% of total carbon required as methane clathrate in a mixed ice clathrate crust. Warm dilute ocean is more likely to result in a convecting crust. In a cold salty ocean, a rigid and conductive crust is more likely. Thicknesses are constrained by thermal conductivity of the crust and composition of the internal ocean. Also, a mixed ice clathrate crust above a cold salty ocean may result in a thermally conductive and rigid crust, which could provide a source of methane in Titan's atmosphere. I'd like to acknowledge my indebtedness to these sources of funding. That's all. Thank you.
Very good. Thank you. Talk is open for discussion. Any questions? Yes, please.
There are studies that show that I mean, when you're dealing with ice convection, that the transition to convective state is subcritical. So in many of these cases, now I don't know, given the composition of the materials that you're working with, if that's the case or not. Have you considered that? And if so, how would that change these figures you're presenting?
Actually, that's a very good question, but I didn't look into that. Definitely will consider it.
Okay.
Thank you.
Just a couple of questions. So there are liquids at the surface. How are you envisioning the clathrates interacting with those liquids?
Can you?
What is the mechanism for liberating clathrates into
we are still
into
working on
Titan's
that.
atmosphere?
We are still working on that.
And have you also considered the role of ethane? There's an interesting paper a couple of years ago by Shukrun et al. Looking at ethane replacing methane in the clathrate cage as one mechanism for liberating methane. And it seems like that would have interesting consequences for your thermal models for the ice.
Yeah, actually, ethane could not penetrate that much, and if ethane is a product of methane dissociation, then it should be confined to a couple of kilometers at most.
Okay. One other question. What range of salinities did you look at for your ocean?
So we used an idealized condition. We considered NaCl H2 system because that's for that system we have.
Sure. I was just
debated.
wondering what was the number for the salinity, just out of curiosity. How much salt?
Actually, so I used a model that was published by Elwood Madden in 2007.
Okay, we can talk offline.
Yeah, sure.
Thank you very much.
Thank you so much.